This is the third video in our introduction to logs. In the first video, we learned how to convert from logarithm form to exponential form and vice versa. In video 2, we learned how to evaluate a logarithm. In this third video, we're just going to clean up a few things and look at a couple basic properties. First off, a common log is a log base 10. The calculator button is automatically base 10, so when you see the LOG button on the calculator, it is automatically base 10. It is called common log because that's the one we use most commonly. So when you see in a book log 100, what it really means is log base 10 of 100, and we can evaluate this because we know that this is asking us what power would we put on 10 to make it equal 100. The power we would put on 10 to make it equal 100 is 2. That means that log of 100 equals 2. And if you used your calculator and you press log 100, it would say 2. Same thing, log 1000 is the same as log base 10 of 1000. And you're saying what power would you put on 10 so that it would equal 1000? You would put a power of 3. So when you just see the word log, that means we're talking about it being base 10. Later on, we'll do more things with the calculator and the logarithm. But right now we're just introducing this definition. So when you see the word log without a base, it is understood to be base 10. There are a couple special properties that we can use to evaluate expressions. Log base a of a to the m just equals m. As long as this base and this base are the same, then your answer is automatically whatever that exponent is right there. So log base 2 of 2 to the third is just 3. Now the reason for that is either that you look at this right here. Forget it's a logarithm and just do 2 to the third. 2 to the third is 8. So now we're looking at log base 2 of 8. So we're saying what power goes on 2 to make 8? 3. The other way to think about this is to take this expression, which was log base 2 of 2 to the third, that's logarithm form, set it equal to x over here. Rewrite this in exponential form. In exponential form, this would say a base of 2 to the x equals 2 to the third. We've already established the fact that if these two expressions are the same and the bases are the same, that means the exponents must be the same, and that's how we get x equal to 3. These two things right here, we're just explaining to you why the property works. You don't need to do all that work. What you have to do is recognize that this and this are the same, and therefore your answer is just that exponent. So this is a very important property to memorize. When you look at this, remember we just said if there is no base showing, it's understood to be base 10. So if it helps you, Andy, you could pencil in a little 10 right here to help establish the fact that this base and this base are the same, therefore it is just that exponent of 5. These two are more complicated, but they still can be done using that property I just showed you. But you have to get this in terms of it being an exponential expression with 3 as the base. So there's two things going on here. You should remember that the square root of 3 is the same thing as 3 to the 1/2. You should also remember that when you have a fraction expression, that means that was really a negative exponent. So this is 3 to the negative 1/2. 1 over the square root of 3 is more simply 3 to the negative 1/2. Now I can use that property because this says log base 3 of 3 to the negative 1/2 means it equals negative 1/2. So how do you know you need to do that? Well, because this is log base 3 and you see a 3 down here, maybe that'll make you think that I should get these bases the same, because if you get the bases the same, you get to use that nice easy property. I see the same kind of thing happening here. This is log base 5. This is a 5 in here. So if I could get this rewritten as 5 to some power, I could use that property. The cube root of 5 is 5 to the 1/3. But this is 1 over that. So this is really 5 to the negative 1/3. It is the log base 5 of 5 to the negative 1/3 gives us negative 1/3. So you get to use that property as long as you can get the expression rewritten so that this base and this base are the same. This is just a little bit different. It's got parentheses, and you know from order of operations you should do what's inside parentheses first. So just pretend that's not even there and just look right here, log base 2 of 8. Hopefully you're comfortable enough looking at this, realizing what you're being asked is what power goes on 2 to make 8. The power that'll go on 2 to make 8 is 3. So now this is log base 3 of 3. It'd be helpful to think of that 3 as 3 to the first so that we had an exponent. Now we can use the property. Log base 3 of 3 to the first is just 1. Same idea in here, start inside parentheses because that's what order of operation says. What power would we put on 2 to make 32? If you don't know what that is, you can use your calculator and do 2 to the second, 2 to the third, 2 to the fourth until you land on 2 to the fifth. Or you can do the successive divisions that I showed you in another video. Keep dividing by 2 and see how many 2's you'd have divided out. But log base 2 of 32 is 5. So this is log base 5 of 5. I'd like to think of it as 5 to the first. That way I get to see that these two bases are the same. Therefore my answer is just the exponent. Another property that's helpful is when this property is written in exponential form. But this is kind of strange because it's exponential form, but it also has the word log in it. This is a raised to the log base a of m. Notice we have that agreement again. There's a base of a, there's a base of a, and look what our answer is, just that exponent right there. So 5 to the log base 5 of 25, as long as those two are the same, we get the 25 there. 6 to the log base 6, those are the same, we get the 36. Now the reason this works is because I can take this expression right here, write it as 5 to the log base 5 of 25, and put equals x. Yes, that has the logarithm in it, but this is actually an exponential expression. So let's rewrite it in log form. The log form of this is going to be log base 5 of x equals the exponent, which happens to be this whole thing. So that says log base 5 of 25. Well, look at that expression. We have log base 5, log base 5. If those two expressions are equal, and they both begin with log base 5, that means that x must equal 25. You don't have to go through all of those steps. That's the whole purpose of memorizing this relationship. This right here, another example, but it is a common log. Notice there is no base, but we know that that's the same as base 10. So we do have our agreement. 10 to the log base 10 of 100 is just 100. There's a couple important facts to emphasize, and that is you cannot take the logarithm of a negative number, and you cannot take the log of 0. Let's try to evaluate log base 5 of negative 25. We know that this is saying what power can we put on 5 so that it would equal negative 25. Well, there is no power you can put on a positive number to make it turn into a negative. We can use a power to make it turn into a fraction, we can turn it into a root, but there is no power on 5 that will make it turn into negative 25. And that's the reason we cannot take the log of a negative number. The reason you can't take a log of 0, same thing. Let's see if we can figure out what power goes on 5 to make it equal 0. There is no power you put on 5 to make it equal 0. So that's why you can't take the log of 0. Another thing we want to introduce in this video is this idea of a natural logarithm. The log function with base e is called the natural logarithm. You know, you can have any kind of base 2, base 3, base 10. Now we're talking about log base e. And it's expressed as ln. There is an ln button on your calculator. You'll do more with the calculator and ln later on. But this is just to give you a couple basics. The domain of the natural logarithm is the set of all positive real numbers, just like it was for the domain of the logarithm function. Here's a basic idea that you might not realize. ln of e, which is the same thing as log base e of e, equals 1. So memorize ln of e equals 1. That's a very useful tool later on when you do some word problems. This right here is just explaining to you why it equals 1. ln means log base e. So what I'm asking for is log base e of e. And we can use our property from a second ago. Think of this as e to the first. We have agreement between these two things, so we get 1. Now another important fact is ln of 1. Think about what this is. We're saying this is log base e of 1. What power would we put on e to create 1? 0. So ln of e equals 1 and ln of 1 equals 0. Memorize those. Those will be helpful to you. The properties we just looked at can be restated using natural logarithms. The ln of e to the m, the ln and the e sort of like cancel out and you just get m. The reason it works is because log base e of e to the m is just an application of that property right there, because I can use whatever base I want. As long as there's agreement of these bases, my answer will just be the exponent. So ln of e to the 12th, you can think that ln and e cancel out, we're just left with 12. ln and e cancel out, we're just left with 7. ln and e cancel out, we're just left with 5x. So that's an important property. The other property that is similar to this one is using a base of e. E to the ln of m is just going to be that m, because the e and the ln sort of like cancel out. What really happens is that, remember, ln is log base e, so here's this property right here. We have agreement of these two bases. So as long as we have agreement of those two bases, our answer will just be this. So e to the ln of 20, think about that canceling, and we get 20. E to the ln of 4x squared is just 4x squared, and e to the ln of 2a is just 2a.